In the last class, we were discussing about how we can represent the state of a system, state of a quantum mechanical system mathematically. So it was given by the first postulate, which says this is postulate 1, postulate 1 of quantum mechanics, which says that state of a quantum mechanical system is described by a vector represented like this uh, in Hilbert space. So we started by uh, answering the question, what is Hilbert space. So in the last class I said that if we need to understand what a Hilbert space is, we need some terminologies. And in last class we studied some definitions, some terminologies such as linear vector space, linear independence, and basis dimensionality. So these definitions we learned in last class. So today also we are continuing in that direction. That is, we are going to learn some more definition. Actually, two more definitions we need to understand what a Hilbert space is. So today we are starting with inner product. Inner product. So inner product is a rule. It is a rule which connects, which actually the actual definition is, or the more technical word is, which maps two vectors, two vectors in a vector space V to a scalar. This can be complex number in general. So inner product is a rule which maps two vectors into a scalar, which means that if there is two vector A and B, this rule connects or maps these two vector into a scalar alpha. Okay. And this rule is denoted like this: A, B. So there are two vectors A and B, and this rule inner product is denoted like this. It says that A and B written like this is equal to alpha. This reads as inner product of A with B is equal to alpha. So this is the notation, and this notation is known as Dirac's notation. And this notation is used in physics, and in mathematics inner product is written in some other way. It is A comma B equal to alpha. So this is also one way to write inner product, and in some cases this notation is more useful, and in some case this notation is more useful. So we will use both these notation, and this notation is Dirac notation. And also this is inner product, but this rule rule which maps two vectors to a scalar must satisfy the following property. Then only we will call it as inner product. So any random mapping, we cannot call it as inner product. This particular mapping should satisfy the following properties. First property is that inner product of a vector with itself must be greater than or equal to 0 for all A in the vector space. So for all vectors in a vector space, the inner product of the vector with itself must be greater than or equal to 0, and it is equal to 0 if and only if A is okay. So this is the first property. And the second property is that the inner product of A with B is equal to the complex conjugate of inner product of B with A. So the order matters. The inner product of A with B is not equal to inner product of B with A, but it is the complex conjugate of other. And the third property is that inner product of A with a scalar multiplied with another vector B inner product of A with a scalar multiplied with B is equal to uh, this alpha times inner product of A with B. Okay, that is, if a scalar is multiplied by this second vector, this scalar can come out. But if this thing is multiplied on the first vector, that is a scalar multiplied on the first vector, then it is multiplied with the second vector or taken the inner product with the second vector, this is equal to alpha star A inner product with B. So this complex conjugate comes from the definition of this second definition or second property. So if a scalar is multiplied with the second vector, that comes out, but if the scalar is multiplied on the first vector, it comes out, but as a complex conjugate. Also, fourth property, it says that uh, if gamma is equal to alpha plus, if C is equal to A plus B, then inner product of D with C is equal to inner product of D with A plus inner product of D with B. So these are the definitions, or these are the properties, uh, the rule connecting two vectors with a scalar must satisfy in order to call it as a inner product. Okay. So these four properties must be satisfied. Okay. And motivated by this definition of inner product, we can uh, define another quantity known as dual of a vector. Dual of a vector. So it is defined like this: for every vector A, there is a corresponding dual vector A defined like this. So this is normal vector. This is a dual vector. And if we define dual of a vector like this, then we can redefine the inner product as, so inner product of A with B, we represent as A, B. We can redefine this inner product of A with B as or equal to definition inner product of B or just product of B with the dual vector of A. So we can redefine inner product as inner product of A with B as multiplication of vector B dual of A. This is normal vector and this is dual vector. So this is a redefinition of inner product in terms of dual vector. Okay, and this is part of Dirac notation, and this vector, this normal vector is known as bra vector, and this dual vector is known as ket vector. So actually reverse, this normal vector is known as ket vector and this dual vector is known as bra vector. And this is known as bracket notation. Bracket notation, which is same as the Dirac notation. So this is the definition of inner product. Inner product is a rule that maps two vectors into a scalar. So this is similar to dot product of vectors in Cartesian coordinate system. That is, if we take the inner product of two vectors, we will get a number alpha, a number. So this is similar to this dot product, but it is a general definition that in the case of this dot product of normal vector in Cartesian coordinate, this is real, but in the case of inner product, it can be a complex number also. So this is inner product, and we will do some problems related to inner product, then it will become more clear. So since we know that it is similar to the dot product, we can, in normal vector, in the case of Cartesian coordinate, using the dot product, we can define the magnitude of a vector, right? So magnitude of a vector A is equal to dot product of A with A, then we will take the square root. So this is the magnitude of the vector, right? So similarly, here also we can define a similar quantity which is known as the norm of the vector. So norm of the vector is denoted like this: double bar norm of a vector psi is defined as square root of inner product of psi with itself. So this is uh, known as the norm of the vector. And if norm of the vector is 1 is equal to 1, then we say that psi is normalized. It is equivalent to say that the magnitude of a vector is unity, or it is a unit vector, that kind of thing. Okay. And also using the dot product in the Cartesian case, we define orthogonality. That is, if the dot product of two vectors is 0, then we say that two vectors are orthogonal. So here also we can say that uh, orthogonality is if two vector A and B, if we take the inner product, if it is 0, then we say that A and B are orthogonal. So if these vectors are both orthogonal and normalized, then we say that it is orthonormal. So two vectors are orthonormal if A B is 0 and A with A is 1 and B with B is 1. Then we say that these vectors are orthonormal. Okay. So if two vectors are no, if one vector is not normalized, we can normalize it. So if uh, a vector psi is not normalized, we can normalize it. How? What we can do is we can divide this vector with the inner product, square root of the inner product, square root of the inner product. Then this new vector is normalized. So this is similar to we can construct a unit vector in some direction by dividing a vector by its magnitude, right? So this is the same thing we are doing. To get a normalized vector, what we are doing is dividing that particular vector by its norm. This is norm. Similar to dividing a vector and a normal vector with its magnitude to get a unit vector. So this process is known as normalization. Normalize. So this is an important process. So up to now, what we learned inner product, and related to inner product, we learned this Dirac notation and the norm of the vector and orthogonality and the normalization process. Okay. And the next thing we need to learn is the completeness of the space. Completeness. So the definition says that if all the Cauchy sequence of vectors in a vector space converges to a vector inside the vector space, then we call that space is complete. Then the space is complete. So what is the meaning of this? It's a Cauchy sequence means a sequence or a sequence uh, which uh, there is actually there is an actual mathematical definition for Cauchy sequence, but that is not needed here. Here, a Cauchy sequence means that uh, it's a sequence where the difference between adjacent elements of a sequence becomes more and more small. So, for example, this is a Cauchy sequence: 1000, 100, 10, 1, etc. So this is a sequence where this difference becomes more small and small, and it converges to 1. So, so this is particular kind of sequence where I am dividing every element by 10 to get some quantity. So this is a particular Cauchy sequence, and if the final element that I am getting is also an element of a space of the same space, then we say that the uh, space is complete. So in this case, this is complete because uh, if we consider the space of a natural number and we will start from some number and divide by 10, uh, this will converge, and the element converging will be also an element in the space, then we say that it is complete. But take another example, this set of all rational numbers. Okay, so this is a space. Rational numbers means numbers that we can write as a fraction p by q. This is not a complete space because I'm just writing a sequence which is 3, 3.1, 3.14, 3.1415, and if we write this sequence which is uh, actually a sequence of all the decimals which eventually converges to pi. So this is a one particular sequence. So uh, the converge this sequence is converging to pi, but pi is not a rational number; it is irrational. So the value to which this sequence is converging is not an element of this set. This is the set of rational numbers, but it is converging to an irrational number. So this is not a complete space. So this is the definition of completeness. And why we are learning all this? Because we need to understand what a Hilbert space is. Okay. So what we learned now, we learned inner product and completeness. Okay. So why this is important? Why this completeness is important? Because there are two things. One, uh, one is that this completeness is necessary uh, for the square summability. That is, this in the second postulate when we learn, uh, we will see that the inner product of two vectors is actually a important quantity, and in order to get a uh, finite quantity, if when we multiply this two, or when we take the inner product of two vectors, if we want to get a finite number, this completeness is important. Okay, so that's why we need completeness. It will become clear when we discuss the next postulates. Okay, so so far what we have learned is, we learned the definition of linear vector space, then inner product, then completeness. So if a set of vectors satisfy all the properties of linear vector space, and all the properties of inner product, and all the properties of completeness, then we call that space or that collection of abstract object as Hilbert. So now we understand what Hilbert space is. Hilbert space is a set of abstract object which satisfies all the properties of linear vector space, and a rule is defined among that vector space which maps into a scalar which obeys all the properties of inner product, and it is that space is also complete. That is, all the Cauchy sequence that converge into a quantity which is also inside the space. Okay, if these three things are satisfied, then we call that space as Hilbert space. And the first postulate says that the state of a quantum mechanical system is represented by a vector, means a vector in a Hilbert space. That is, the vector satisfy all the properties of linear vector space, inner product, and complete. Okay, so this is first postulate. That is how we can represent quantum mechanical state mathematically.